Welcome, everyone. This is the new episode of the UK podcast, Turbulence at the Exascale. I am Sylvain Lézé from the Department of Aeronautics at Imperial College London. This podcast has been designed in order to gather the view of the turbulence community regarding exascale computing and trying to identify the challenges and opportunity associated with exascale computing. This podcast is part of the UK initiative called ExCALIBUR, which is led by the Met Office, the UK Atomic Energy Authority, and the UK Research and Innovation. And its aim is to deliver research and innovative algorithm developments to harness the power of exascale computing. So we are currently several working groups working towards various applications, and I'm leading the group on turbulence. And I'm also the lead of the UK Turbulence Consortium. So this podcast is part of the UK Turbulence Consortium and the ExCALIBUR project. So what we are trying to do, we're trying to see what's going on also in other countries. And today we are going to see what's going on in Spain with our guest, Esteban Ferrer, who is a reader in applied mathematics at the School of Aeronautics in Madrid. So good afternoon, Esteban.
Good afternoon.
So Esteban has research interest in CFD, of course, and in particular around high order methods like discontinuous Galerking. He has also interest in aeroacoustic bluff body flows, turbulence modeling, flow stabilities, renewable energies, and aeronautics. So it's going to be very nice to have a chat with him today. Right, so let's start, Esteban, by asking you the first question. And for those who don't know you very well, maybe, please can you tell us more about where you are from, what you have studied, and how did you end up at the School of Aeronautics in Madrid?
Okay, Sylvain, thank you very much for the invitation. Well, I have a bit of a weird background myself, right? So I will go through it. I started mechanical engineering at the School of Industrial Engineers in Barcelona. So I'm originally from Barcelona. And then in my final year, I had the opportunity to do a double degree in Toulouse. So I went to Toulouse to do aeronautics, and that gave me a double degree. And there's where I got interested into fluids, because that was the specialty really there. So for my final degree, I went to Imperial College, where I did my final degree on numerical methods with Joaquin Peiró. And then I decided to go to industry. So that's where the not really typical background starts, right? So I went to industry for 2 years as a CFD consultant in the UK. And then I moved to Spain, to the Renewable Energy Center in Spain, and to work with wind turbines, all related to CFD. And so after 6 years in industry altogether, I wanted to do a PhD because I wanted to get deeper into the numerics. And I decided to go to Oxford to do a PhD there on developing my own solver with the idea of simulating wind turbines and tidal turbines of vertical axis. So I developed a discontinuous Galerking solver to do that. So after the PhD, there was an opportunity to go to Madrid as a postdoc in a Marie Curie project, and there's where I've been since 2012, I think it was. So then I became a lecturer, and then now I'm a reader in applied mathematics. So this is a little bit, it's a bit different background because people tend to go to industry for maybe 1-2 years, but I was in industry for quite a bit and then decided to go back to academia. So,
Great, thank you very much. So you said you've been in the School of Aeronautics in Madrid for quite some time now, and my next question is: now that you have these experiences in academia and in industry, what's the best thing about your current position, and what's the best thing about working in the School of Aeronautics in Madrid?
Right. So I think about academia, what's very nice is that you can explore new fields of research, right? So you have this flexibility of looking into new things. Of course, there's also the very attractive thing that you can travel and work with people all around the world, which is not so easy when you're in industry. And you can go deeper as well in some fields that you couldn't do in industry. So in industry, everything has to be kind of fast, right? You need answers for yesterday, and you don't get to look into things a bit more deeply. So I think that's one of the things that drove me to go into academia after industry, and I think one of the things that I really like about academia, that you have flexibility. Regarding the School of Aeronautics, I think I must say this is one of the best schools of engineering in Spain. And then I get the opportunity to have brilliant students. So, and this is a very, very nice thing to have, right? I always get surprised how good they can be, right? Because you propose a topic of research, and they are almost independent, and they provide you with answers and things, which to me it's amazing, right? And we're talking undergrad there.
Yeah, of course.
So this is very nice. I would say there's a bad thing about being in Spain at the moment, and it's that there's not much money for research. So it's very challenging to get grants in Spain for doing research, right? So apparently this is something that might change in the future, but right now we mainly rely on European projects and European money. And as you know, it's very competitive. So it's a bit difficult at the moment.
Good. Well, thank you very much for this answer. Moving on, could you tell us on what project you are working on at the moment?
Okay, so I'm mainly interested in two big research lines, right? So one is this continuous hierarchy in high-order methods. So for those who don't know, this is like a finite volume method, but then you can enrich the polynomial space from constants to arbitrary polynomials inside each element. So this is one line of research. The other one is stability sensitivity analysis for flow control. The idea is to do flow control. I'll tell you a couple of things about this. So about this continuous hierarchy, so this is a fairly mature method, I would say now. So we're able to do quite a lot of things, but there's two research lines that are still open, right? So one is multiphysics, so adding more complexity to the solvers. And for this, in this line, we're working on acoustics, we're working on flow structure interaction using immersed boundaries. We're looking on multi-phase flows, right? So that's a little bit of multiphysics we're looking at. Everything, of course, in the context of higher order methods. The other one is to make the solvers faster, right? And to make things faster, to get calculations done fast, what we do is we concentrate in local P adaptation. So as opposed to using a polynomial which is homogeneous in the whole mesh, we refine with a higher polynomial order in some of the elements to get a better solution. And there's multiple ways of doing that. We focus on truncation error estimates, which is one particular line. I have a few papers on that. And so on top of that, so this is to increase, let's say, the spatial speed of the simulation. Then we also concentrate on the temporal side. And for this, we develop matrix-free and matrix forming methods and multigrid. So this is the things we're doing now. Regarding stability sensitivity, the ideas there are to use the sensitivity analysis, which basically provides you some gradients of the sensitivity of the flows of particular forcing or particular deformations in the geometry. And then we try to couple this information to optimizers, such that we use the information coming out from this mathematical formulation of the sensitivity to optimize or to derive new geometries. The advantage of this is that we don't need a particular functional, a classic functional to do the optimization. We don't rely on lift or drag, but we can pinpoint flow features, right? So stability will give you a mode which is associated to a particular flow feature, and based on this particular flow feature, we can optimize to reduce it or to increase it or whatever. Very recently, we started looking at some things on machine learning and coupling both with DG and with analysis of flow structures. So this is very recent stuff. Right, and so these are the projects, these are the topics we look at. And then what we have recently seen is that there's quite a lot of interest from industry in developing or understanding or start using higher order methods, and particularly DG. So we have some collaborations with aircraft industry, with wind turbine industry, and with oil and gas. So the multi-phase, for example, solver we developed recently, it's for oil and gas industry. So you can have three-phase flows and things like that. And also, so this is the end user, and also we work with CFD developers, and because they have increased interest also in high-order methods. And this is in terms of courses that we give to them and collaborations as well to help develop their own solvers. But I will say that now it's very interesting time to be doing high-order methods, because there's a lot of traction from industry as well at the moment, which wasn't there a year ago. So
good. Thank you very much. So you mentioned, well, you're doing a lot of DG development and research, and I believe everything is embedded in your flow solver called HORSES 3D. So for the people who are going to listen to this podcast, can you tell us a little bit more about this HORSES 3D code? I mean, how big it is, and which language are you using, and what type of flow you are studying?
okay, so HORSES in particular, as you mentioned, we're putting a lot of effort now in developing HORSES. So HORSES started a while back with a collaboration we had with David Kopriva from the States, who is a little bit one of the, I would say, the main developers of DGSEM, which is a version of DG that we use, which is quite efficient, right? And that works very well with the hexahedral elements, so structured hexahedral elements, and that's a very efficient DG sub method, we'll say. So all started with him, and we've been adding new features to the original solver, right? So, for example, well, as I mentioned, this is a high-order solver, so you can increase the polynomial to arbitrary degrees. And arbitrary typically means that we run things between P5-ish polynomials, or between P5 and P10, right? The nice thing about the solver is that normally in high-order methods, you get exponential decrease of the error, but you also get a almost exponential increase in the computing time, right? But with the DGSEM, or at least in our solver, what we see is that we get an exponential decrease of the error, indeed, but we get a linear increase with the polynomial of the computational costs, which means that, well, with a little bit of more expensive computations, we get a much better solution. So from that starting code, we've been adding functionalities, and well, as I mentioned, one of the things we are now quite interested in is local P adaptation. So we can anisotropically, change the polynomial order in each direction, and we can couple this with anisotropic multigrid, which makes things quite efficient. Finally, I mean, this DGSEM can have some instability issues when we go to under-resolved LES simulations. And for this, we implement and we develop also some energy entropy stable schemes, which are very popular these days because they do enhance the robustness of the schemes, especially for under-resolved simulations. So
thank you.
This is a little bit about. Sorry, the language is in Fortran 2003, and that's historically because at the School of Aeronautics we teach Fortran, so most of our students know Fortran. And also because David Kopriva, who's a little bit who helped us starting developing this, also used Fortran. So it's a little bit of history.
Thank you. Thank you. And I have a follow-up question, just curiosity. So you're doing work around wind energy or tidal energy. So I was wondering, how do you model the blades and the turbines?
Right. So so there's various ways of doing it. So back in the days when I was doing my PhD, I developed a sliding mesh technique, right? So with a sliding mesh, you can take into account the rotation of the blade explicitly. And this is what I did back in the days. Right now, we don't have the sliding mesh technique implemented in HORSES. That was another solver that I developed back in the days. and we haven't migrated this part, the sliding mesh part, to horses. It shouldn't be difficult, but we haven't done it. So right now we have looked at actuator lines and actuator these simplifications for this. We're trying to do some work along these lines as well.
Great, thank you. Let's talk a little bit about the polarization strategy in this code. So is it based on MPI, or is there any other options? Can you tell us a bit about that?
Yeah, it's hybrid MPI OpenMP. So you can use both. You can use both. And the test cases we've run, which weren't super big, but they show weak and strong scalability, which was good for high polynomials. So if we go, and I think that was up to 2000 or something like that processors. So not a huge amount, but the scalability was pretty good, especially when we went to hybrid MPI OpenMP and very high polynomials. So the larger the polynomials, the better the scaling. And this is due, I think, to the locality, right, of the degrees of freedom in terms of the elements. Because you have the very high polynomial order inside each element, so these are all localized degrees of freedom that only interact locally. You don't need bigger stencils or anything like that. So I think this is very good, and this is especially good if we use explicit schemes. So with the explicit schemes, we get a lot of advantage of very good parallelization, I would say.
Great. And if you were to, so you say the code is scaling very well up to about a few thousands core, and is there any plan to go beyond that, or to rethink the parallelization strategy?
Yes, of course, but we need less. So the systems we have right now, we have a small cluster of computers at the school, which we own, so we can do anything with it. We have Madrid, which is a cluster of the UPM, and then we have access to the RES, which is the Red Española de Supercomputación, which is you can ask for computing hours at a national level. And this is competitive, but it's not super difficult to get hours there. So we need to access facilities, of course, that allows us to run in many processors. And so far in Spain, of course, it is Mare Nostrum, which is the highest. And then the rest are not that big. So we can, of course, try to run in many more processors, but we have to find the supercomputers to do it. The big challenges, I think, for us to go in a larger scale is first load balancing. When we think of p-adaption, right, we would like to do dynamic p-adaption. Then, of course, load balancing becomes a real issue, right? And this is something we haven't really looked at properly, especially for large systems. So I think there's very nice ideas around where you can think of the load balancing on the fly. So you keep thinking and looking at the system and doing the balancing on the fly. But I don't think that nothing of that is easy to do. And then I guess one of the problems we have with horses is it's a general tool, right? So it's a general framework where we can do explicit, implicit, a variety of polynomial orders. There's various multiphasic things that we included, and this is good because it's a very general framework to do maths, algorithms, and things like that. It's not so good, in my view, to do high performance computing, right? Mm-hmm. Because things change drastically if you are in P8, polynomial 8, or polynomial order 2, right? And then you might optimize for low polynomials, and you don't get performance at high polynomials, or vice versa. So this is, to me, a little bit of a bottleneck that we have right now, right? So for which particular combination of things do we optimize our things in thinking of exascale, right? So I think for this, the idea will be maybe to give the power to the optimizers, right? And there's some clever optimizers that, depending on the parameters you have, they do things. But I mean, we haven't looked at that at the moment.
Great, thank you. I forgot to ask you, I'm also a big fan of Highorder methods, and I was wondering why you decided to go for high order DG methods.
Okay.
What was your thinking process about that?
Okay, so that was a bit out of luck, I will say. I mean, when I started my PhD, I was a finite volume guy, right? So I didn't know much about high order. I read a couple of things, but nothing about DG for sure. Right? DG back in 2008, I think, when I started my PhD, it wasn't very popular, to be honest. And then in the lab in Oxford, there was another PhD student who's now a lecturer in Australia, who was doing shallow water equations, and for this he was using DG, right? So DG for hyperbolic equations like shallow water is very good, very efficient, and I would say easy-ish to use and to code. And so he convinced me that was the very nice method. No, I was coming from a finite volume, and that was like a finite volume, but on top of that, you could increase the accuracy at will, right? So that seemed like ideal. And then I got into that, only that I was trying to solve the incompressible Navier-Stokes equations, which are slightly more complex than the shallow water equations, I think, and with sliding meshes and a bit more complexity. So, but well, I think when you're young, you are a bit naive, and you get involved into things that you don't know where you are going. But it turned out okay. So I managed to get a solver that was working, and it was very interesting. And it got me into discontinuous quadratic, which turned out to be a very good option.
Yeah. Good, very interesting. Now I have a more general question. I mean, you are more familiar than me about the Spain turbulence community, and I was wondering if you could give us your opinion about the readiness of the Spanish community regarding exascale computing. I mean, you have Mare Nostrum, which is a very nice system. And do you think that the turbulence community is ready to use a very large system like Mare Nostrum, and even systems that are maybe 10 times or 100 times bigger than Mare Nostrum?
Well, I don't think the Spanish community is ready, but I don't think any community is actually completely ready. So in that sense, we're probably not behind other countries. That being said, I think there's probably, from my view, a couple of bottlenecks, right? So one is pre and post processing of the data, no, and the solutions we get. So in that sense, we are working on feature extraction, as I mentioned before, right? And these kind of techniques can be stability analysis or can be BOD, DMD kind of methods, right? So and with this, one can try to extract flow features on the fly. To not having to allocate that much memory. And then there's a pre-processing as well, which is hard. So constructing the meshes in an efficient way, and then distributing them across many processors. That's a challenge as well. And also, I mean, one of my concerns as well is hybrid systems. So maybe because I haven't fully tried to exploit them completely, but to me, because we are more concentrated in the algorithms, right, that go into the system, we would like to have the compiler to do the optimization for each hybrid system, right? I personally don't want to have to worry about, okay, now I'm running with this hybridization, CPUs, GPUs, etc., and now I'm changing, and I have to be careful with, I don't know, many of the issues that you can get related to memory and stuff. I would like all these to be transparent, right, to me as a user. Of course, I think there's tools that do that, but I'm not sure what's the level of maturity of these tools, especially thinking of exascale computers. So, I mean, I'm open to ideas along these lines.
Great. My next question is a very hypothetical question. If you were to be able to use efficiently an exascale computers tomorrow with your code, what will you do? I know you mentioned that you are interested in adding more complexity and things like this, but can you elaborate a little bit more about what would you do with a super large supercomputer?
Okay. So I think there's very nice things what one could do if you could get a simulation very fast, right? So one of the ideas could be, for example, optimization, right? So if you can do optimization of entire aircraft using LES, and furthermore, trying to do the optimization in almost real time. What I mean is, okay, I'll try this parameter. So multi-objective optimization, right? So you try this parameter, you get an optimized geometry, and then you add another parameter, and you get another optimized geometry. Of course, this within hours, not within months, right? Which is, I think, more or less the current state of the art. So this, to me, would be ideal, and that would be a massive improve of all the tools we have and the interest of industry. I think industry will then become completely interested in using large systems, in using LES and optimizers and things like that for their developments, the day-to-day developments. So this is one thing. Another thing we could think of is optimization of wind farms. I think you have worked a little bit on optimization of wind farms, which I think is very interesting work. Perhaps one could think of including, multi-phase to mimic the free surface and see what happens with rough seas and things like that, which I think that depending on how you model the free surface, that's a very big challenge these days. And trying to do optimization with including all this physics, it's really, really difficult. So I think these are two things that I would really like to see during my career. We'll see if this happens.
Great, thank you very much. And I have one final question. So we are talking a lot these days about exascale computing, and I was wondering, what do you think will happen after that? I mean, do you think we are still going to be dealing with CPUs and GPUs that are going to be more powerful, more energy efficient? Or do you think at some point in our career, we will have to completely redesign our solvers because we are going to be dealing with completely new hardware technology? What's your view on that?
I guess the answer is I have no idea. I think it's a very interesting question, and I have no idea. And I think the having no idea, it's logic, because I didn't have any idea about GPUs 15 years ago either, right? And GPUs weren't developed because of our science, the science we do, but because of the video games, right? So who knows if in 10 years there's another technology that the kids like, right? And that makes develop some new architecture that we don't kind of think of. So I think it's because what's driving the real development is not really what we do. I think we can expect anything. I honestly don't know. I do think the hybrid systems are going to be the future, though, at least for the next 10 years, right? So
yeah.
So we need to try to do something with that, and hopefully, as I was saying, trying to use optimizers to do it for us. So this is what I would like at least.
Yeah, well, I think this is what everyone wants.
yeah. So.
Thank you, Esteban, for your answers and for your inputs and for your time, of course. And we also would like to wish you all the best for your software development and all your stability analysis. It's very, very interesting. Thank you very much, everyone. That's it for today. As usual, I will be putting the links on our Twitter, UK Turbulence, and you can find all the podcast recordings on the UK Turbulence Consortium website. So thank you, Esteban, for your time.
Thank you.
And everyone, see you soon for a new episode of the podcast Turbulence at the Exascale.